No problem.
Okay, good morning, Mehta sir.
Good morning.
Good morning.
Yeah.
Sorry for being late.
No
As
problem. No problem.
That was a small meeting with Honorable Vice Chancellor. That's why I was late.
No problem, sir.
Shall we start now?
Yeah, definitely, sir. Definitely.
Okay.
Okay.
So, very good morning, all of you. As the chairman, on behalf of our Kavitri Bahinabai Chaudhary, North Maharashtra University, Jalgaon, I heartily welcome today's external referee, Professor Jignasu Mehta sir from Department of Chemistry, MK, Bhavnagar University, Bhavnagar. Equally, I welcome all participants who have joined this PhD was online. Guide Dr. CJ Patil, the candidate Mr. Sanjiv Salve, and all other colleagues, faculties from Muktainagar College, other affiliated colleges from our campus who have joined online for this PhD house. So with the kind permission of external referee Mehta sir, I request the today's research student who is going to present his work. I request him to present his work within half an hour. So Mr. Sanjiv Salve,
Yes, sir.
you start now and try to complete within half an hour.
Yes, sir. Yes.
Okay, sir.
Okay.
Yes. Good morning, everyone. Sir, whether I am audible, sir?
Yeah.
Good morning.
Yes.
And welcome to my final Viva-voce. First of all, let me thank you to all for coming here today. And I must take opportunity to welcome Professor Dr. P.P. Mahulikar, ex-Pro VC and Head Department of Industrial Chemistry, School of Chemical Sciences, KBC, NMU, Jalgaon, and Chairman of this committee. Professor Dr. J.P. Mehta from MK Bhavnagar University, Bhavnagar, external referee, and Professor Dr. S.S. Rajput sir, BOS chairman, and our acting principal, Professor Dr. H.A. Mahajan, and my research guide, Professor Dr. C.J. Patil, and all of you. Let me introduce myself. I am Sanjiv Salve from Srimati Khadse College, Muktainagar, affiliated to KBC NMU Jalgaon. In my presentation, I would like to report on synthesis characterization of chromium, cadmium, Schiff-based complexes and evaluation of their catalytic activity, which is the title of my thesis. The present slide shows the registration details. I registered in 2013, but due to angioplasty in 2014, the work get delayed. But I am thankful to university authorities and my research guide to give me a moral support and motivation to continue the work. And I submitted in January 2021. In my presentation, I'll focus on three major issues. That is synthesis of ligands, synthesis of cadmium and chromium complexes, and their catalytic activity towards benzyl and amyl alcohol. I have organized this talk in a following way so that I have divided my presentation into 7 chapters. First, introduction, then literature review, experimental characterization, catalytic activity, results and discussion, summary and conclusions, and finally the future scope. First of all, I'd like to give you an overview of chirality, different types of catalytic reaction, oxidation reaction by chiral Schiff base. The present slide shows what is a Schiff base and Schiff base applications in a different fields. Here, Lord Kelvin in 1884 in Baltimore lecture stated that I call any geometrical figure or a group of points chiral and say that it has a chirality if its image in a plane mirror ideally realized cannot be brought to coincide with itself. And you can see here the pair of enantiomers as well as a racemic mixture. So these figures are here. Then moving to next, hence we have to design and synthesis of a high catalytic activity and ensure selectivity of chiral catalyst is one of the hottest research topic, and so that chiral Selen can induce a high stereo selectivity for organic transformations, and that's why we go through this work. This slide shows the different types of catalytic reactions. Uh, these are Diel-Sulder, epoxidation, oxidation, Hague, Michael addition, aldol condensation, polymerization, and so on. These different types of the reactions are the catalytic reactions. So again, it is a hottest topic, or we can say the current topic for the research. Then here we know the process of photosynthesis, which is done by the plants, and through that, though the term oxidation equally well known in both organic and inorganic chemistry, the present chapter has a major concern of oxidation of various organic substrates and synthesis of many biological active compounds, pharmaceuticals, fine chemicals, dyes, plastics, food additives, and fabrics have been involved through oxidation reactions. Moving next, that is, this slide shows the percent of active oxygen in oxidizing reagents. Here you can see that S2O2 shows the 47% of active oxygen, and co-product is water and becomes eco-friendly, so it is used. This slide shows the non-chiral skip base of metal complexes and chiral skip base of metal complexes. The work is done by Razul and others, while in chiral skip metal complexes, the Jacobson catalyst is a well-known catalyst, and the work done is more. The catalysis is high on approaches to minimize the grain chemistry, or say E factor. So nowadays field has changed. Catalysis becomes a driving force for organometallic compounds. Nowadays major research has been going for the development of sustainable methodologies and to find a better alternative for the traditional methods. This slide indicates or provides information about types of catalysis and their characteristics, and some examples of the type of catalysis. There are two types: homogeneous catalysis and heterogeneous catalysis. And so moving through the literature, we come to the justification that the main validating aim of the present research is to demonstrate the importance of the organic synthesis and its scope with numerous properties against biological, medicinal, pharmacological, catalytical, agriculture, as well as the industrial fields. And by interpreting the endurance of current situation, here we prepare compounds such as say SSN bis 3,5 dibromo salicylidene 1,2-dicyclohexane diamine, abbreviated as a L1, SSNN bis 3,5 diiodosalicylidene 1,2-dicyclohexane diamine, which is abbreviated as a L2, and SSNN bis 3,5 ditertiary butyl salicylidene 1,2-dicyclohexane diamine, it is abbreviated as L3, and their cadmium second and chromium third complexes, that is of total 6, are expecting to examine their catalytic activity towards oxidation of benzyl and amyl alcohol. The upcoming 4 slides are the representative slides, which shows some researchers who made their efforts towards a Selen type of the complexes. On the basis of the literature survey, we were able to decide the problem, main objectives of the present investigation, and the methods of synthesis of ligands and complexes, and how the study the catalytic activity, the derived complexes, and finally conclude the work done. So these 5 slides are the contribution of genuine scientists towards catalytic activity. So let's now look at the slide which shows the main objectives of the present investigation. which were targeted by following literature glimpses. So these are our main objectives, that is synthesis of some chiral skip bases of symmetrical skeleton, including salicyclotype, synthesis of complexes from these symmetrical ligands, to characterize the ligands and their cadmium second and chromium third complexes, and to arrive at their structural peculiarities, to study the application of the synthesized complexes as a heterogeneous catalyst in oxidation reaction, and to compare behavior of oxidation and aromatic and aliphatic alcohol towards above catalyst. This slide shows our work sequence, that is synthesis of skip bus ligands, then synthesis of cadmium complexes, synthesis of chromium complexes, their characterization, and finally to study the catalytic activity of the skip bases and their complexes. Now moving towards the experimental. Our experimental chapter is divided broadly into 3 sections. One, which is details of the reagents used and various analytical or physicochemical techniques we have used. The details of the synthesis of chiral skip bus ligands and their complexes. And finally, we are dealing with the catalytic study and the different analytical methods used for the catalysis. The table on the slide shows the important chemicals which are used by its make, molecular formula, molecular weight. Generally, we use Sigma Ulrich, Merck, SD Fine, Ranchechem, and Spectrochem like that. So these are the various chemicals that are used. Then we move towards synthesis. Ligands, complexes, all these are prepared according to the published methods. Whether it will form or not, that will be monitored by using a PLC. Then the present slide details the procedure, preparation of ligands L1 and their CD and CR complexes. So here preparation of L1 is like this: a solution of 3,5-dibromo hydroxy benzaldehyde in ethanol is mixed with a solution of 1,2-diaminocyclohexane in ethanol, and the mixture was stirred reflux for 2.5 to 3 hours. The yellow wet crude material form was filtered and recrystallized from ethanol. It was dried in vacuum desiccator. The good results are there. Preparation of CDL1, that is a solution of L1 that was added to the solution of say cadmium chloride, and then pH is adjusted as 7 to 8. The mixture was magnetically stirred, reflux for 2.5 to 3 hours. Then the brown to yellow powder is formed. It is filtered up. Again, here there will be a good result for us, good yield for us. Then preparation of CRL1. The method is one and the same for CDL1. Using L1 that was added into the chromium third chloride hexahydrate solution. Then pH is adjusted at 7 to 8. The mixture was magnetically stirred and reflux at 2.5 to 3 hours. The dark brown powder is formed, and again here again yield is too good, about 77%. So this is about the preparation of L1, CDL1 and CRL1. This present slide details the procedure, preparation of ligands L2 and their cadmium and chromium complexes. I already described in details about the procedure of L1, CDL1 and CRL1. Now here the process is one and the same, only the substitute get changed, that is bromo to iodo and iodo to tertiary butyl. So I am not giving much more time to this, and moving with a kind permission of say chairman and external referee, we can move this, sir.
Yeah, go ahead.
Yes, you can go ahead.
Okay, sir. Okay, sir.
You try to cover only your work, synthesized work, detailed work we have already seen in the thesis. So you can major achievement and your catalytic activity, you can give more emphasis to that.
Okay, sir. Okay, sir. So this slides indicates the preparation of L3 and their cadmium and chromium complexes. This is about the catalytic activity. Here, lot of work is done by Laro and Jacobson. This slide provides information about materials used and experimental setup of catalytic activity and additional confirmation test for the formation of benzaldehyde or oxidation of benzyl alcohol. And from this, this is our first step, that is the synthesis of the ligand. This is our second step, that is the preparation of complexes. And this is our third step, where the catalytic activity towards a benzyl and amyl alcohol that should be studied. That was studied, sorry. Then the current slide indicates the various analysis, that is the primary and secondary of ligands and complexes, and where the analysis was done. Generally at SEP Kochi, Sri Reliable Industrial Laboratories at Jalgaon, then ISER Bhopal. This gives too much help to us, and characterization would be done here. Then this is about the characterization. This current slide shows a physical and analytical data of chiral skip bases L1, L2, and L3. So here you can see that the molecular formula, structure, molecular weight, its color, its RF value, and range of the melting point, and the moving phase, that is ethyl acetate and N-hexane 4:1. Then this is a photographic representation of chiral skip bases and the TLC. Then this is our elemental analysis. In elemental analysis of this ligand L1, L2, and L3, these are in agreement with those of calculated for the expected molecular formula for ligand L1, L2, and L3. It is given on the slide. Then moving to the characterization, or we can say the UV visible and FTIR spectral data for chiral skip base ligands. Here the FTIR and say UV visible spectrum is given, which shows pi to pi star transition and n to pi star transition, and FTIR frequencies in a centimeter inverse. So these are the graphs of say UV visible as well as FTIR for L1, L2, and L3. Then we go for H1 NMR spectrum of chiral skip base ligands L1, L2, L3 recorded in DMSO. So these are the various signals that are observed and various peaks at various peaks, which signals are observed. The details are given here for L1, L2, and L3. Then I think it is repeated. This is HRMS, which indicates the calculated values and found values, which are strongly reveals and predict the molecular formula for L1, L2, and L3. And these are the structures from all above characterization when arrives at the following structures of the ligands, say L1, L2, and L3, which are depicted here. Now, the primary characterization of complex, say CDL1, CDL2, and CDL3. Here, this current slide again shows structures, molecular weight, color, and its yield of say complexes of cadmium. Then this is a pictorial information or photographic representation of say CDL1, CDL2, and CDL3. Then this is the elemental analysis, which is in the agreement of calculated for the expected molecular formula for CDL1, CDL2, and CDL3. Then these are the UV visible and FTIR spectral data for cadmium complexes, showing pi to pi star and n to pi star transition, and FTIR frequencies in centimeter inverse. Again, this is a UV visible and spectral data. This is about H1 NMR of say CDL1, CDL2, CDL3. Then this is a HRMS for CDL1 and CDL3. Again, this is for a chromium complexes. Then it is a photographic representation of chromium complexes. It is a elemental analysis. Then this is a UV visible and FTIR spectrum for CRL1, CRL2, CRL3. This is the H1 NMR spectrum for, and this is the HRMS of CDL3. These are the structures. After characterization, we can draw this one for chromium and cadmium complexes. And now we are moving towards a catalytic activity. Here, first of all, we optimize the reaction parameters, and so that the choice of solvent that should be more important. And for that purpose, we use methanol, ethanol, acetonitrile, BCM, DMSO, and we get good results for acetonitrile, and that's why here the acetonitrile is optimized. After that, quantity of solvent, we tried for 8 ml, 10 ml, 15 ml, 20 ml. By keeping all parameters, all reaction parameters constant, we vary the quantity of solvent and we get good results at 10 ml. And again, optimization is done for the quantity of solvent is at 10 ml. Then effect of temperature. By keeping all reaction parameter constant, 3 to 3 Kelvin, 343 Kelvin and 363 Kelvin. We tried this, and at 343 Kelvin we get a good results. Again, 343 degree Kelvin is the optimum temperature for this total reaction. Then influence of amount of catalyst. Here we use, by keeping all reaction parameter constant, changing only the amount of catalyst, 0.03, 0.05 and 0.7 gram, we get a good results at 0.05, and that's why the 0.05 is the optimum amount of the catalyst. And effect of variation of time, from 1 to 4 hours we carried the reaction, and at 4 hours we get a good results. That's why we optimize the time at 4 hours. And effect of H2O2, we tried as 1:1 ratio, 1:1.5 and 1:2 ratio. We get a good results at 1:1.5, and that's why 1:1.5 ratio, if for the effect of H2O2 concentration is taken, and that will be optimized. In this table you can see here we choose a solvent acetonitrile, quantity of it which is a 10 ml, 343 degree Kelvin, catalyst amount is 0.05, time 4 hours, oxidant amount 45 millimole and substrate amount 30 millimole. So these are the optimum reaction conditions for the oxidation of benzyl alcohol, and accordingly we set out these results. And here you can see that the catalytic activity of the prepared cadmium second and chromium third complexes are screened for their activity towards a benzyl alcohol oxidation reaction. The conversion rate of benzyl alcohol to benzaldehyde is more in CDL1 than in CDL2 than in CDL3. The same trend will be carried in chromium complexes. Then it is due to the say bulkiness of the group, because bromine is less bulky, iodine is more bulky, and tertiary butyl is again more bulky, and that's why the steric hindrance and other things that are very say complicating the reaction, and that's why the good results are get at CDL1 and say less to CDL2 and less to CDL3. Same will be happen for the chromium also. Therefore, the catalyst CDL1 is more effective than CDL2, and CDL2 is more effective than CDL3. Same thing will be happen in case of CR. L1 is more effective than CRL2, and CRL2 is more effective than CRL3. Again, here one thing is noted that if we compare cadmium and chromium complexes, it is marked that cadmium complexes are less effective than chromium complexes due to the position in periodic table, variable oxidation state, that is chromium ranging from +2 to +6, while cadmium shows only +2nd oxidation state and behaves like a group second A. And again, it affects reactivity, size of chromium and cadmium also. Then looking to above discussion on catalytic activity of synthesized complexes on benzyl alcohol, the possible mechanism for the benzyl alcohol to benzaldehyde oxidation reaction is as depicted here. Here the catalyst activation done by S2O2, there is a formation of intermediate first, then this intermediate first, or we can say the adduct first, on dehydration converted to oxo intermediate second, and this oxo intermediate second reacts with a benzyl alcohol and get converted to intermediate third, proton shifting from aldehydic oxygen to hydroxyl attached to central metal atom. Intermediate 4, this intermediate 4 on dehydration gives the product aldehyde. This is a detailed scheme, and this is a shortened scheme of the reaction, catalytic reaction. Then, sorry, the catalytic oxidation of benzyl alcohol in a solvent was studied using hydrogen peroxide as the oxidant and cadmium second and chromium third complexes as the catalyst. Many research groups have developed different catalytic methods for oxidation of benzyl alcohol to benzaldehyde. Among the various methods, transition metal Schiff-based complexes catalyzed oxidation is important. Generally, benzyl alcohol oxidation gives benzaldehyde, benzoic acid, and benzyl benzoate. We haven't detected any benzyl benzoate. The reaction was highly selective towards benzaldehyde. Slight amount of benzoic acid is also formed. Recently, few studies have mentioned that there is a strong impact of nature of organic or inorganic solvent on the oxidation of benzyl alcohol process. Now we move towards a catalytic activity of cadmium and chromium complexes towards amyl alcohol. So here again we set out the reaction parameters, and for that the choice of solvent, again whatever the process we have followed for benzyl alcohol, that process is followed here. And here say methanol, ethanol, then acetonitrile, DMSO, these solvents are used, and we finalize the acetonitrile because we get a good results in that. Then for the quantity of solvents, 8 ml, 10 ml, 15 ml, 20 ml that are used, but we get a good results at 10 ml. That's why it is finalized or optimized. Then effect of temperature, when we are talking about effect of temperature, 323, 343 and 363 Kelvin we have tried, but we get a good results at 343, and that's why the temperature is optimized at 343. Effect of amount of catalyst, here we tried for 0.03, 0.5, 0.7 gram of the catalyst, amount of catalyst. We get good results at 0.05, and then again the amount of catalyst is optimized at 0.05. Then moving towards the effect of variation of time, we tried for 1 hour up to 4 hours. We get a good results for 4 hours, and that's why the effect of variation of time, or we can say the time that should be optimized at 4 hours. Effect of H2O2 concentration, again it is 1:1 ratio, 1:1.5 and 1:2. we get a 1:1.5 ratio is where we get a good results at that position, and that's why we optimize that one at 1:1.5 ratio. And now the this table is showing the choice of solvent is acetonitrile, solvent quantity 10 ml, temperature 343 Kelvin, catalyst amount 0.05 gram, time 4 hour, oxidant amount say 45 millimoles, and substrate amount 19 millimole. So this will be given here. Here, the conversion rate of amyl alcohol to amyl aldehyde is more in CDL1 than in CDL2 than in CDL3 due to the presence of bulky group and stirring hindrance in CDL3. The same trend will be carried in a chromium complexes. The product that is a pentanol is obtained with the help of catalyst CDL1, more in CDL1 and less in CDL3. Again, it is due to the presence of bulky group and stirring hindrance. The same trend will be carried in chromium complexes. The byproduct pentoinic acid and amyl pentoinate are still obtained, but less in amount or even latter is not detected. So this is about that one, and this is say we optimize for this one and we applied for the remaining catalysts. Now looking to the above discussion on catalytic activity of synthesized complexes on benzyl alcohol, the possible mechanism for the amyl alcohol to amylaldehyde oxidation reaction is depicted here. The catalyst activation done by S2O2 and forming intermediate first, then intermediate first on dehydration converts to oxo intermediate second. The oxo intermediate second reacts with a benzyl alcohol and get converted to the intermediate third by proton shifting from aldehydic oxygen to hydroxyl attached to a central metal atom. Intermediate 4 is there, and this intermediate 4 on dehydration gives the product aldehyde. Here it is a detailed scheme, and this is a shortened scheme of that one. So here this is the solvent-free catalytic oxidation of amyl alcohol studied using a hydrogen peroxide as the oxidant and cadmium chromium complexes as the catalyst. Generally, amyl alcohol oxidation gives a amyl aldehyde, pentoinic acid and amyl pentoinate. We haven't detected any amyl pentoinate. The reaction was highly selective towards amyl aldehyde. A slight amount of pentoinic acid is also formed. Several research groups have developed different catalytic methods for oxidation of amyl alcohol to amyl aldehyde. Among the various methods, transition metal, Schiff-based complexes, complex catalyzed oxidation is worth mentioning here. Then we move to next. We skip this chapter because the characterization of say that will be discussed here. So chapter 6 is coinciding with 4 and 5. So we are skipping this one. We have already talked about it. And finally, summary and conclusion. So here, summary is that details of the studies of the synthesis or spectral characterization of catalytic applications of some metal complexes of chiral Schiff bases derived from 3,5-dibromo, diiodo and ditertiary butyl salicyldehyde separately with 1s, 2s, 1,2-diaminocyclohexane are presented in this thesis. The present thesis is divided into 7 chapters. I have already detailed about these chapters. That is, chapter 1 is about introduction, chapter 2 about literature survey, chapter 3 is experimental work, chapter 4 deals with primary and secondary analysis, chapter 5 is deals with catalytic activity, chapter 6 is deals with analytical and spectral characterization discussion, and finally this chapter is say summary and conclusion. So our conclusions are that the three Schiff bases were synthesized as per the literature, and the newer chromium and cadmium complexes were synthesized and characterized by analytical and spectral methods. The molecular formula of the complexes were calculated from the elemental analysis data, and that should be found to be L1CDCl, L1CrCl, L2CDCl, L2CrCl, L3CDCl, and L3CrCl. The molar conductance and magnetic susceptibility data shows the electrolytic nature and magnetism behavior respectively of all the studied complexes. These chiral Schiff-based ligands were used to synthesize complex with cadmium and chromium ions in a moderate to good yield. The structure of the complexes were confirmed by the spectral characterization. Complexes of chiral Schiff-based ligand based on the characterization included the attempts to prepare a corresponding cadmium second and chromium third complexes of chiral Schiff bases were successful. The different substituents, that is bromine, iodine, and tertiary butyl, on the ligands and the soft and hard metal ions did not significantly affect the structure of these complexes, but do affect their catalytic properties, which is well done by the overall size of the catalyst. For the cadmium second and chromium second complexes of L1 to L3, the outcome, that is the catalysis of the benzyl alcohol and amyl alcohol in presence of S2O2 and in acetonitrile as a solvent, results are in the following order, that is CDL1 is better, say best than CDL2, and CDL2 again better than CDL3, and the same trend will be carried in chromium complexes, which is attributed to the substituent present of the ligands and their atomic size. The catalysis indicated that the rates are higher for chromium third complexes as compared to cadmium second complexes, which might be due to the activity of the metal in the complexes studied. For the metal complexes of L1 to L3, the bulkier tertiary butyl in the ligand results in a more hindered structure of the complex containing L3 ligand, which is in case of the complex containing L1 ligand. The substituent bromide is comparatively smaller in a size, and hence the complex synthesized bromide is smaller in size, and hence show a higher rate of catalysis of primary alcohol in presence of H2O2 in an acetonitrile as a solvent. In this study, the catalytic activity of synthesized cadmium second and chromium third complexes in the oxidation of benzyl and amyl alcohol were tested. The cadmium second and chromium third complex of Schiff base L1, L2, and L3 exhibit better catalytic activity. Detailed investigation was carried out by varying the amount of this complex, temperature, then amount of solvent, time, then with aqueous 30% H2O2 as the oxidant. The complex was found to catalyze the oxidation with more selectivity for benzoic oxidation products than that for the benzoic acid. The lower H2O2 efficiency observed for this reaction might be due to the greater catalytic activity of the complex towards the decomposition of hydrogen peroxide. Again, these are some trends. That is, the conversion rate of benzyl alcohol to benzaldehyde is more in CDL1 and less in CDL3, and the same trend will be carried out in a chromium complexes, and it is due to the bulky group and steric hindrance in CDL3 as well as in a CRL3. In case of cadmium complexes, desired product, that is benzaldehyde, is obtained with the help of catalyst, is more in CDL1 and less in CDL3. Same trend will be observed in chromium complexes. Again, it is due to the bulkiness and steric hindrance, which is because the ligand involved are the same, and the only change is the involvement of chromium instead of cadmium as a central metal ion in the catalyst formation. Hence, the trend is one and the same. Therefore, the catalyst CDL1 is more effective than CDL2, and CDL2 is more effective than CDL3. Same say trend will be carried in chromium complexes. If we compare cadmium and chromium complexes, it is marked that cadmium complexes are less effective than chromium complexes due to the position in periodic table, variable oxidation state of chromium, which ranging from +2 to +6, while cadmium shows only the +2 oxidation state. Catalytic activity towards amyl alcohol. Again, here the same trend, that is for benzyl alcohol, it will be carried out. That is CDL1 is better and CDL3 is say less effective due to the bulkiness and steric hindrance. Same trend will be carried in chromium complexes, and the product, that is the pentanol, is obtained with the help of catalyst is more in CDL1 and less in CDL3. Same trend will be carried out in chromium complexes. The byproduct pentoinic acid and amyl pentoinate are still obtained, but it is in a less amount or even in a say not detected. Comparison of this one, say cadmium and chromium complexes. We earlier stated that the cadmium and chromium complexes we observe, and cadmium complexes, they are less effective than chromium complexes due to the oxidation state. Chromium ranging from +2 to +6, their size, reactivity, and other things. Finally, we concluded that oxidation of benzyl alcohol is good in comparison of amyl alcohol with the help of chromium and cadmium complexes. In aliphatic, oxidation is less, while in aromatic it is higher. The higher the expectation of CDL3. Exception, that is CDL3. This is what we think about. For future work, the catalytic properties of these complexes for polymerization and oxidation reaction in different systems and conditions should be studied. Also, the effect of other substituents such as strongly deactivating group, strongly activating group, suitably located on the ring for a strong interaction with metal second and third ion, and complexes with other forced to transition metal ions also should be systematically studied. It is of interest to study more geometrically flexible speed bases such as those obtained from diaminocyclohexanes and substituted salicylaldehydes, as these are expected to lead to reversible redox properties. Other than as a catalyst, other potential use of this material should be studied. Examples are say spintronic, electronic, and photonic materials. By studying their electronic transition, fluorescence, and phosphorescence respectively. These are our publications from the thesis work. Then this is a publication other than thesis work and the conferences participated and attended. This is the list of say institutes and list of dignitaries, those who support me during my work, those who help me during my work. Their contribution is say very valuable contribution. So I'm most thankful Professor Dr. V.L. Maheshwari sir, Vice Chancellor of the KBC NMU Jalgaon. Then Professor S.T. Ingle, Professor Pro VC of KBC NMU Jalgaon. Professor P.P. Patil, ex-VC of KBC NMU Jalgaon. Professor Dr. P.P. Maulikar sir, now he is a chairman of this committee and ex-Pro VC of KBC NMU Jalgaon. Professor Dr. D.H. More, Dr. Nitin Patil, Aizer Bhopal. The person helped lot to us. Dr. S.S. Rajput sir, Dr. Gunwant Sonone sir, Dr. Nilesh Pawar, our Honorable President, Sau Rohinitai Kharse Khevalkar, our ex-principal Mr. V.R. Patil, our acting principal, Dr. Mahajan sir, Dr. Manisha Patil from Bendale College, Jalgaon. Then Sep Kochi again plays very vital role or very important role for the investigation. Then Mr. Anil Vispute, he gives a good reports and help to us. Mr. Jinendra Jain, the provider of chemicals. And finally, where I'm work all these, Dr. C.N. Hete, head of the chemistry department, teaching and non-teaching staff of the chemistry department in Khadse College, Muktai Nagar, and unstoppable help of Dr. Anil Shinde, Dr. Kolte and Dr. and Deepak Tadele is there. And finally, I am not going to complete the work when I have done an angioplasty, but my guide say help me much more, and he gives me a moral support, and that's why I could done this work. So I am very thankful to Dr. C.J. Patil, who is my research guide. And it is not last but least, I heartily thanks to those who supports me unstoppably, directly or indirectly, and my whole family. I thankful to all these persons, institutes. Thank you very much. Thank you, sir.
Okay, Mr. Sanjiv Salve, you have presented it very nice within a given time, the brief account of your research work. So, firstly, I request the external referee, Professor Mehta sir, to interact with the student, whether he has any questions and suggestions and remarks also.
Yes, thank you very much, sir. Mr. Salve, you have done good work and you have contributed towards the some heterocyclic, heterogeneous catalysis. So this is a good thing. But one or two things I would like to ask you. The thing is that why you use chromium and cadmium only, not any other metal ions? What is your aim behind this chromium and cadmium?
Sir, as we gone through the literature, the less work has been done on cadmium and chromium complexes in comparison with other metals, and for the and as we go through the literature, we see that we can do the work on it, and that's why we choose with the help of my guide, we choose this topic.
Second thing, that is two more important parameters regarding the catalytic activity, that is turnover frequency and turnover numbers. I think that you have not mentioned anywhere in your presentation. What have you heard about this turnover frequency and turnover numbers regarding the catalytic activities of this?
No, sir.
These two parameters are good to indicate whether the catalyst is catalyst is how much active or like that. Turnover frequency and turnover numbers. TOF, it is called TOF and TON.
Yes, sir. Yes, sir. Yes, sir. We are not focused on it, but just we go through the HPLC because it is easy to say for analysis, because it is the lab is decided at Jalgaon, and that's why we tried for that, sir.
Okay, I understand that it is a bit difficult for you to perform this type of and the third thing is that some of the references it is found, it is duplication is there. So this reference before that duplication of the references are noticed by me, so such things should be avoided in future also.
Yes,
okay,
sir.
Otherwise your work is good. I congratulate you that you have done good work regarding the catalytic activity. And the thing is, one thing is that what are the any side product is there, or 100% conversion of aldehyde to alcohol to aldehyde?
No, sir. No, sir. There are some side products are also there, sir. Only the say I mentioned in the say final conclusion. Just I show you. 1 minute, sir.
Okay, I think it is the major product is this aldehyde, I think.
Yes, yes.
Yeah. But then you have to be sure about the that remaining product, that side product will not interfere in that particular convert at the time of final product separation. How you mean, what steps you have taken that the final product separation of the final product is the desired product only?
Sir, we are not tested for the interference of the remaining one, but we have tested that there is the final product benzaldehyde and benzaldehyde and amaldehyde. We have tested for that one. We have not tested the other interference of the byproducts.
Yeah, no. Okay, no problem. I think this is sufficient for you from my side.
Okay, sir. Thank you very much. With this continuation, after external referee Mehta sir, I would like to discuss with student about some points. You have mentioned in introductory part that chirality is the most important for activity, no?
Yes.
Why chirality? Non-chiral compounds are not active, showing activity.
Yes, sir. Both they are showing the activity, but non-chiral is too good for that one. That's why interference and steric hindrance will be less at that.
What about yields? If you use chiral catalyst and non-chiral, is there any effect on yields of product?
May, sir, but we are not focused on that one.
Okay, okay.
And
In your synthesis, in general procedure, you have mentioned 50 millimoles, 86 milligram diaminocyclohexane, benzaldehyde 420 milligram. You are carried out the reactions with such a small quantity.
yes, sir, we carried out reaction on that quantity.
420 milligram benzaldehyde. And how will you have prepared then ligands, complexes? Mahajan sir, mute करा, unmute करा, Mahajan sir.
Mahajan sir,
Unmute करा.
Mahajan sir.
My question is, Salve sir.
Yes, sir. Yes, sir.
You have carried out synthesis with 420 milligram, 86 milligram. Then how you have performed that formation of complexes, ligands? What was your yield?
Our yield is in milligrams, sir.
No, that is not my question. If you see the preparation of, see on slide, preparation of CDL2, CDL1, CRL2,
yes,
you have used 400 milligram.
Yes.
Huh?
Our yield is 434 milligram for CDL2.
No. Yeah. Original compound that you are synthesizing that ligand, no?
Yes, sir.
So how much?
Yes, sir.
What your product of 200? That 434 milligram, no?
Ligand
CDL2. The yield was 434 milligram, 89%, no?
for complex.
So how you have managed with such a small quantity for characterization and applications?
Sir, for characterization, we are not getting too much amount of the product, whatever the complex is there. We get limits for the characterization, and that's why some characterization remains undone. Those we want to do, but due to the say not getting more yield, or we tried at a small level. That's why
Yeah.
we are not able to do the whatever we want to do. That 2, 3 characterization we
Even in synthesis of ligands, in synthesis of complex,
yes,
yield is always overall less than 90% in your synthesis.
yes sir, yes sir,
Not a single compound have yield more than 90%.
yes sir.
Why? Why? You have not tried to get higher yield, or what is your observation in a literature document that reported yields by other chemists or authors?
Um,
It is like this yield, or that is more than your yields?
No, sir. It is uh, we we tried say we reflux for 1 hour, 2 hour, 3 hour
Okay.
like that, but we are getting good results in 2.5 to 3 hours, and that's why we make a trial, some trials, and after that trials we say set out the refluxing time, and accordingly we get the yield.
In catalytic activity, you have mentioned whatever complexes, CDL1 is more active than CDL2, CDL2 is more than active CDL3. In this way, for chromin also, no? And what you have said, it is because of steric hindrance.
Yes.
Only steric hindrance is factor, or any other electronic factor also involved in this activity?
Yes, their oxidation state is again in cadmium and chromium. The oxidation state is again say play a role. That is, cadmium shows only +2nd oxidation state, while chromium ranging from +2 to +6, and that's why cadmium complexes are less effective, while chromium complexes are more effective.
Okay. You have oxidized benzyl alcohol, amyl alcohol by using H2O2, no?
Yes, sir.
By using prepared ligands.
Yes, sir.
So, what is your observation? Have you tried in absence of ligand as a catalyst, only with H2O2 oxidation? What is the exact effect of your ligand? Have you studied?
No, sir. We are not studied like that.
Without ligand, only oxidation with H2O2. It is a common organic oxidation, no?
Yes, sir. Yes,
So with H2O2, then with H2O2 plus your ligand.
sir.
You have not studied that.
Not studied, sir.
Okay, okay. You have studied effect of solvents, and you found that acetonitrile is a good solvent than methanol, ethanol, no?
Yes.
It is your observation with amyl alcohol oxidation to aldehyde, huh? Can you justify that acetonitrile is better than ethanol and methanol? Then I have studied amounts, volume of solvent, 5, 10, 20, 30, 40 in this way.
Yes.
Huh? 10 ml, up to 10 ml solvent, you obtain better yields.
Yeah.
After increasing solvent, that yields are decreased.
Somewhere, sir.
Somewhere. But why these yields are decreased? Can you guess about the reason behind that?
No, sir, we are not tackled about it. That where we get a good results, carry and optimize the reaction.
After increasing the volume of solvent, only one possibility, that is the solubility.
Yes.
Because of solubility, then in catalyst, you have studied 0.03, 0.05, 0.07 moles
Yes.
for catalyst. That you have studied. And in time for the reaction, you have studied 1 hour to 4 hours.
Yes, sir.
And you have mentioned at 4 hours, we obtained higher yields.
Okay, sir.
Oh, but what about after 4 hours? Have you studied for 5 hours to get again higher yield?
We moved whenever we are optimizing that one. When we move above 4 hours, um, uh, results are not too much changing.
Okay, remain constant. That's why you have mentioned 4 hours is the optimum period for the reaction to get higher yields. No? Am I correct?
Yes, sir. Yes, sir.
Yeah. So you should mention that after 4 hours we have studied, but yield remains same. That is important. You have not shown your publications outcome in the form of presentation in conferences. How many publications you have?
2 publications, sir.
2 publications. In which journal?
In Journal of, say, 1 minute, sir. In IJRAR in April 2019, and one is from Oriental Journal of Chemistry.
Okay. And what about remaining work to be published from thesis? How many papers will be published now from remaining work? 2, 3, 4?
Minimum 4 to 5 papers.
4 to 5. It is my suggestion.
Yes, sir.
Now go to good journals for remaining work publication.
Yes, sir. Yes, sir.
Now you have no hurry to get any something. Already you have achieved the last period you have. Now you will be getting a PhD degree.
Yes, sir.
So instead of publishing this nice work in Oriental Journal of Chemistry, this type of journal, it has not good reputation. So take your way, time, but publish instead of 4, 5 papers, just 2 papers in good journals.
Okay, sir. Okay, sir.
That will be more credited. Huh?
Yes, sir, definitely.
So very nice presentation, very nice interaction. So with the external permission of external referee, shall I conclude, sir?
Yes, sir. You can conclude. And I'm really thankful to you, all the members, that you have given the opportunity as an external referee here. And I'm congratulate Mr. Salve for his very good presentation. Thank you very much, sir.
Okay, thank you very much. So with the remark of external referee, on behalf of second external referee who has evaluated thesis from the Maharashtra. So today, Mr. Sanjiv Salve has nicely presented his research work, nicely answered the questions raised by external referee as well as chairman. So with the kind permission and the appreciation of both external referee and from internal referee, Dr. CJ Patil, I declare hereby that the PhD degree should be awarded to Mr. Sanjiv Salve of Kavitri Bahinabai Chaudhary, North Maharashtra University, Jalgaon, in the subject of chemistry. So from this moment, Mr. Sanjiv Salve is Dr. Sanjiv Salve. Hearty congratulations.
Yes, congratulations, Dr. Sanjiv Salve now.
And equally, I congratulate his guide, Dr. CJ Patil, as he has guided him for a proper constructive outcome. So I congratulate Dr. CJ Patil also for additional one more PhD student.
Congratulations.
I thank all delegates, participants online for this PhD waivers. So with this concluding remark, I thank you all. Thank you very much.
Sir, 1 minute.
Thank you.
CJ Patil.
In hurry, we left out welcome you. Initially, when you have started the meeting,
Yeah.
Your welcome, we could not make it today
Okay.
as per a regular function. So I congratulate both of you, or I thanks to both of you to be here. Mr. J.P. Mehta, Dr. J.P. Mehta, who was my colleague at the initial stages
Okay.
of his job. I was
Ah,
at the same university, Bhavnagar, and at the same juncture, we could meet on the online platform. We'll try to meet somewhere in short time.
Okay.
I thanks to our college also for giving this opportunity and to stand behind us for the work, for day-to-day working, and good support from the university peoples. And as far as the other team is concerned, we are very thankful to be present in this Viva time. Thanks to all. With the
Okay.
chair permission, kind permission of chairman, I declare now that the meeting is over.
Or but
Thank
CJ
you, sir.
Patil, just send report to the Mehta sir after having his sign
Okay,
and
okay.
scan copy. Then send
Okay.
one person in the university so that I will sign and forward to the research section.
Yes, sir. Yes, sir.
Okay. Okay. Thank you, sir.
Yeah.
Thanks a lot.
Thank you very much.
Thank you. All the
Sir.
best.
Shall we close meeting? Okay.
Yeah, yeah. Now we should do.
Okay, okay.